Good afternoon, folks. How are you today? We are in lab number 5. In this lab, we are going to discuss fully annealed plain carbon steels. So, we are going to talk about metallography, microstructures, and noob hardness. I'm going to break the video up in 3 parts. In the first part, we are going to look at the theory in which we are going to study the eutectoid reaction in iron and iron carbide phase diagram. Then in the second part, we are going to learn how to metallographically prepare a specimen for microscopy to distinguish microstructural features. And this is going to be a long video because there are many steps in preparing the specimen for microscopy. And then in the third part, we are going to look at the microstructures of these steels under an optical microscope. We are going to reconcile the image analysis that we are going to do with our theoretical calculations. And we are also going to measure noob hardness and determine the hardness of each microconstituent. Okay, so let's see. Let's first look at pure iron. So when we look at pure iron, that means it has no carbon in it, 0% carbon. Its elastic modulus is 30 million psi. Then if we add carbon in the range of 0.02 to 2% by weight, we have what are called plain carbon steels. So this is an alloy where we are dissolving carbon interstitially in iron. So notice this is a very small amount and it does not change the elastic modulus at all. It means 30 million psi. And then if we add more than 2% carbon, we get cast irons. And again, elastic modulus doesn't change. Let's look at yield strength. Annealed pure iron has a yield strength of 5,000 psi. It's really fairly soft. If we add even just a tiny amount, 0.1818 weight percent carbon, that's our 1018 steel, even in annealed condition, it has a strength which is 4 times higher. And we know that by strain hardening it, and you're going to soon learn how by heat treating and phase transformations, we can increase this yield strength to almost 80,000 or 100,000 psi. Cast irons, even the most ductile cast iron, has a yield strength of about 100,000 psi. So you see what just tiny amounts of carbon can do in terms of strength. It can increase the strength considerably. Now let's see what we can do by looking at the phase diagram. So we call this iron carbide phase diagram because we have this metastable phase iron carbide which has a composition of 6.7%. Even though it is metastable, unless we raise it to high enough temperature, this carbide remains in this iron carbide form. So for practical purposes, it is stable. So that's why artificially we draw a iron carbide, even though it is not a stable phase diagram. This phase diagram has 3 reactions, so as to say a peritectic reaction here at high temperature, which is of no use. So we cannot exploit this peritectic reaction for several reasons. First of all, it is high temperature and it has very low carbon. So it is not useful. Then at an intermediate temperature range here from 2% above 4.3% or so, we get a eutectic reaction. And this eutectic reaction happens in steel having more than 2% carbon. So this is where cast irons come in. So in cast irons, we exploit the eutectic reaction. Then we come to this low temperature reaction, which is called eutectoid reaction. And you can see it starts from about 0.022% and goes around 0.76, which is a important composition, to about 2%. And this is where we have steels. So at the low end, we have low carbon steels. At middle end, we have mid carbon steels. At high end, we have high carbon steels. So we are going to exploit this eutectoid reaction. Notice this reaction occurs at about 727 degrees C. So about 700 degrees C. And the eutectoid composition is 0.76% carbon. So we are going to talk about different phases in steel. Remember, phases are where we have a volume of material that is at same state, solid state in our case, same composition throughout, and same crystal structure throughout. So in this iron, in the steels, we are going to look at four phases particularly. Ferrite, which is body-centered cubic, and at 723 degrees centigrade, its solubility limit is 0.022. It is very soft and it is stable at room temperatures, in a range of temperatures, I should say. Austenite, which is called gamma, is face-centered cubic. At 723 degrees C, its solubility is 2%. It is medium hard and it's also a stable phase. Cementite, the third phase, is iron carbide. It is face-centered orthorhombic and it has a fixed composition, 6.7% carbon. It is extremely hard. Theoretically, it is metastable, but for practical purposes, it stays for such a long time at low temperatures that we consider it a stable phase. Then another phase that we are going to talk about in our next lab is martensite. It is body-centered tetragonal. It can have a range of percent carbon, typically from 0.02 to about 1%. It is also very hard phase. It is metastable, forms upon quenching the steel from high temperatures. And again, metastable means unless we raise the temperature considerably, for all practical purposes, it is a stable phase. So here is that left-hand corner of the iron carbide diagram, the eutectoid reaction. So notice that at high temperature, we have gamma phase. So if we take a steel that has this eutectoid composition, this 0.76%, and we cool it at high temperatures, it'll be all one phase, all gamma austenite. And then as we cool it very, very slowly, just below 727 degrees at this point B, it should split up into these two phases, alpha ferrite and Fe3C cementite. So above eutectoid temperature, point A, it is all austenite. Below point B, it is ferrite and cementite. Notice different crystal structures and they have different compositions. So in your phase diagram portion of the course, you have been taught how to read up. You draw a tie line. So we started with 0.76% carbon. By drawing the tie line, we find out composition of the ferrite is 0.022% right here. And cementite, which is 6.7%. So let's write down this reaction. So we have gamma splitting into alpha and Fe3C. Of course, this composition we started with was 0.76% carbon. This is 0.022% carbon. This is 6.70% carbon. Of course, we started with 100%. And let's suppose we end up with W alpha percent of alpha and W Fe3C of the cementite. So what we can do is, you can of course use your tie line and draw that, but often it is easy to just remember. We have 100% of 0.76% carbon, so that is how much carbon total we started with. We will have W alpha times 0.022, that much carbon in alpha, WFE3C times 6.7, that much carbon from cementite. So you can see we have two equations, one equations, but we have two unknowns. But we know that these two are related. So we know that WFE3C is 100 minus W alpha. So now we have two equations, two unknowns. And we can solve for both of them. So the easiest is to just substitute this here, right? So we will get what? 100 times 0.76 is 0.022 W alpha plus 100 minus W alpha times 6.7. So now we have one equation, one unknown, and we can solve for W alpha, right? So we will get 100 times 0.76, and we can bring this to the left hand side, minus 100 times 6.7 is 0.022 minus 6.7 W alpha. So now we can solve for just W alpha. So I use my calculator. So I have 100 times 0.76 minus 6.7 divided by 0.022 minus 6.7. And I'll get 88.9, which I'm going to round up to 89%. So our Fe3C would be the remaining 11%. So that's the answer we get. Okay. So let's see what the structure looks like. So as we see that this austenite has to split into two widely varying percent carbon phases. We have a lot of this alpha, which appears as white in this micrograph. So everything that is white is ferrite. And these dark layers are cementite. So this layered structure is called pearlite. So pearlite is a two-phase structure. And specifically, they have 89% ferrite, 11% cementite, and they are in alternating layer form. So by using this word pearlite, we are saying all these things. So we give this a name, the structure. So we have 100% pearlite here. Okay. So now let's look at off eutectoid structures. So for instance, let's consider a carbon composition to the left of this eutectoid. So in this case, what will happen is we start cooling at point point C, we have all gamma. Then at point D, we are in two-phase region, we will have alpha and gamma. So the alpha that we get here is called pro-eutectoid alpha. It formed before eutectoid temperature was reached. So now we have two phases. And notice right above the eutectoid temperature, this gamma would be of eutectoid composition. So as soon as we cool it slowly, just below the eutectoid temperature, this gamma is going to become entirely pearlite. So we will have essentially two structures in our micrograph. We'll have this pro-eutectoid alpha. Notice that this is in this kind of a pink layer form. Of course, the color is just to highlight it. And the remaining was gamma, now which has become pearlite. So let's see if we can identify it. So here is our structure. This is of 0.38% carbon. So our alloy had 0.38% carbon. So here again, you can see we have these white areas, these white blobs. These are called pro-eutectoid ferrite. And then we have these dark regions, and you can see somewhere these alternating layers are resolved. In some places, they are not resolved. So it depends just on the thickness of those layers. If they are very thin layers, they may not get resolved at this magnification. So if you were to kind of eyeball it, I would say maybe half, 50% is pro-eutectoid ferrite and 50% is this pearlite. That would be my eyeball estimate. Later on in the lab, we are going to use image analysis to identify how much is dark area and how much is white area. We will try to do it. We'll see. We'll need very good images for that though. But let's do our microstructural analysis. So now what we have is we have gamma that has split into pro-eutectoid ferrite and pearlite. So this we started is 0.38%. We know alpha just below is 0.022%, and we know this is 0.76% carbon. So we started with 100%. This is the composition, remember. This is the amounts. We want to find out how much alpha and how much pearlite we will have. So again, we can write our equation. 100 times 0.38 is equal to W alpha times 0.022. And now we know that we can write 100 minus W alpha, because that's how much pearlite we will have, times 0.76. So again, we have one equation, one unknown. We solve for W alpha, we will get 51%. We solve pearlite would therefore be 49%. So remember, we estimated roughly 50-50, and this is what our calculation shows us. Okay, let's see to a composition on the right hand side of eutectoid composition. So on right hand side of O here, let's say we pick up a composition like 1.2% or something like that. So at point G, we are in one phase region. Again, we have just austenite. When we cool it through, this is called the ACM temperature line. At point H, we will have this cementite precipitating out. So these are these black blobs kind of. Rest of it is austenite. So just above the eutectoid temperature, this austenite would be of 0.76% composition. And of course, cementite is fixed, 6.7%. So when we cool it slowly below the eutectoid temperature at point I, all of this gamma is going to transform into perlite. So we will end up with two structures. We will have this cementite and we will have perlite, which is two-phase structure. So again, let's look at our microstructure. So this one has 1.4% steel. And you can see what we have is we have this white, which looks like a river. All of this river is pro-eutectoid cementite, and rest of it is perlite. So if I were to estimate, again, I would say this white river constitutes about 10%. So 10 and 90%. But let's see what our reaction shows us. So we started with austenite at high temperatures. Our alloy composition was 1.4% copper. It has split into pro-eutectoid cementite, which is 6.7% carbon, and perlite, which we know is 0.76% carbon. So we started with 100% of gamma. Let's say we have this much of Fe3C cementite and this much of perlite. So again, we can write 100 times 1.4, and this time let's convert this into Wp. So again, we have one equation, one unknown. We can solve for Wp. We will get 89%. So 89% is perlite. And of course, the remaining would be this pro-eutectoid cementite. Okay. Remember that if it is a tiny amount, then we will see them as these little bubbles. This is what we are going to see in the second part. So there you have it. These are all called annealed steels because we are cooling them very, very slowly. So again, as a summary, what happens? When we have a eutectoid composition steel, we cool it very, very slowly, we will get 100% perlite. If we have a hypoeutectoid steel, steel containing less than 0.76%, we will get a combination of pro-eutectoid ferrite and perlite. If we take a hypereutectoid steel, cool it very, very slowly, a steel that has more than 0.76% carbon, we will get this pro-eutectoid cementite and perlite. So usually we will have lots and lots of perlite in a hypereutectoid steel and small amounts of pro-eutectoid cementite, this white river. And this is very, very hard. Now this kind of a structure is not very good because it is going to be brittle. So remember, you have a very brittle, hard layer that is connecting the entire cross section. So if a crack were to happen, it is going to propagate very quickly through this channel. So this structure is not very good mechanically speaking. Okay.